So folks, we're continuing our pre-work. We're now going to move on to section 1.5. And in this section, we learn completely how to solve linear first-order equations, which I think is actually pretty exciting. So we're going to learn how to solve the linear first order. And so just as a reminder, we saw in our work from Wednesday's class that the linear first order ODE is one that can be written in this form. So I've written it in terms of the y prime term and the y term, and notice that when I separate it, I put it in that format. Notice that y prime is a linear term and y is linear, not in terms of t, but in terms of the variable y. I'm not squaring y, I'm never dividing by any y's. I've put it in this form, and these terms are all linear for y's and y's derivatives. So this is our definition of a first order linear equation. Just as a reminder, these a's of t's and b's of t's, those don't need to be linear in terms of t, or I guess maybe I should have put this, if we're using x as our independent variable, maybe we could write dy dx is equal to, plus a sub x y plus b sub x, so or is equal to b sub x. So here I've just replaced the independent variable with x instead of t. But anyway, when I talk about this being a linear ODE, I'm talking about the linearity in terms of y and not necessarily x or t. I'll put t here since that's how I first wrote this. Okay. All right, so how are we going to solve the linear first order ODE? What we're going to do is we're going to do something very clever with the product rule from differential calculus. And then what we're going to do is we're going to multiply both sides of an ODE by what we're going to call an integration factor. And this integration factor technique reminds me something of like the complete the square technique that you used in algebra. That is, we multiply both sides of this equation by the integration factor, and that allows us to fold up the left-hand side as a product rule here. And we're going to see that here in just a second. Before I do so, I want to remind you of your product rule from Calc 1, and that said if you had the derivative, we'll do d dx, of f times g, that you could rewrite this as f times g prime of x plus g times f prime of x. And we are used to always taking something, a product of two functions, and then applying the product rule to it to expand it out and actually compute those derivatives. When we do the techniques that we use in this method, we're going to force ourselves to look at something that looks like the right-hand side, and then we're going to factor it up like the left-hand side. Don't worry if this step confuses you. We'll talk more about it in class, but for right now we want to actually just practice that step. The next thing is, when I get ready to solve this, is I need to put it into a particular format. So I'm going to take this ODE. It is a linear first order. It doesn't quite look like that yet. Notice there's no coefficient in front of the y prime here. So let me put it into that form. So I'm going to divide both sides by t. So it gives me y prime minus 3 over ty is equal to t to the fourth. By the way, here we're making the assumption that t cannot be 0, and just as we did in the last case, we should always be on the lookout for singular solutions. And in fact, y equals 0, well, actually it's not in this case, but you should always be on the lookout for singular solutions whenever you start dividing by variables in this class. Okay, so now that I've put it into this format here, notice that this is in the form y prime plus p sub x y is equal to maybe f sub x. Or I guess I'm using t's here, but you get the point. I've got some function right here in front of my y term. Okay? The integrating factor that I'll reference is mu sub x equals e to the integral of p sub x dx. This is going to be that integrating factor that I'm going to multiply to both sides of this equation. So here we go. We're tackling this problem. The first step is to find, well, actually first put it into linear form. So we put it into linear form. That's what we did in this first step right there. And the next thing we're going to do is we're going to compute the integrating factor. So mu sub t, in our case, mu sub t is the e to the integral of minus 3 over t dt. So the who's playing the role of that p function that's right in front of the linear component y? It's, in this case, it is that minus 3t, and so that's what I'm integrating and then raising that over the power of e. And so if we do that computation, when we go ahead and compute that, we're going to end up with e to the minus 3 ln of the absolute value of t. And folks, technically there's a plus c here, but we've got some latitude because there's actually many integrating factors that'll work. So I will always, for this, pick c equal to 0. And so our integrating factor, mu sub t, is equal to e to the minus 3 natural log absolute value of t. Next, what am I going to do? Well, I'm going to go ahead and see if I can simplify this, which I can. I can rewrite this as e to the natural log of the absolute value of t to the minus 3. And then that simplifies to just be the absolute value of t to the minus 3. And then here we need to make some sort of assumption. Let's assume t is greater than 0. And that's related to the fact that we divided by t over here. We broke up the solution for the interval for which this solution would exist into two pieces. So assuming t is greater than 0, we get the mu of t is equal to t to the negative 3. So, and we're working through these steps. We put it into linear form, and then we computed the integrating factor. Okay, so I know this is a little bit disconcerting because I'm just sort of telling you what to do. We're going to derive this whole process in class. But what I'd like to do now is we're going to multiply both sides of this equation by that integrating factor. So when I do so, let's go back to, here's our equation. I'm going to multiply each side by that integrating factor. So when I do so, I've got t to the minus 3 times ty, oops, I need to be in that linear form, y prime minus 3 over t y is, and then that's equal to t to the minus 3 times t to the 4th. And if I clean up this mess, what I end up with is that t to the minus 3 y prime and then minus 3t to the minus 4 y is equal to, and then on the right hand side we end up with just a t. Okay, why have we done all of this work? Why have we done this integrating factor technique? Well, look what we have on the left hand side here. We've got an expression, t to the minus 3, and right over here is that expression's derivative. Likewise, we've got an expression, y, and right over here is that expression's derivative. If you look above here, that should look very similar to the product rule from differential calculus. That is, here's my first derivative of the second, and then I've got plus my second derivative of the first. And so this is just a product rule, so this whole thing can be written as ddt of my first, which was t to the minus 3, times my second, which is y, and that's going to equal t on the right-hand side there. Okay. And folks, I'm a little bit out of room. I apologize for that. I'm going to scoot over. I'll give you more room in this handout. And we'll go ahead now and integrate both sides. So if we integrate both sides, we've got the integral of d dt, t to the minus 3y dt, is equal to the integral of just t dt. Well, this is saying find an antiderivative of the derivative of this expression. So by the fundamental theorem of calculus part 1, that's just t to the minus 3y. And on the right-hand side, we get 1/2 t squared, and here's where I'll put that arbitrary constant. So in the process of solving this for y, we're going to divide both sides by t to the minus 3, or multiply both sides by t cubed. And so it gives us y sub t is equal to 1/2 t to the 5th plus ct cubed. And there we have our, in fact, it turns out in this case, the general solution to this on a given interval. So in this case from 0 to infinity, or from minus infinity to 0. So folks, I'm going to redo a problem just like this. I know that was a little bit challenging. We've worked through one of these. I'm going to do a similar problem here in the next example. We're going to practice this again, and I hope it becomes a little bit more straightforward in that second example. So join me in the next video, and we'll continue along. And let me know if you have any questions on this.